here at Safran Federal Systems, we specialize in GNSS and PNT simulation for U.S. defense, military, any kind of environment that you can think of. And along with that, we provide specific test systems for CRPA, or what you might call SERPA, Controlled Reception Pattern Antenna systems. And that requires specialized simulation systems. And we call this the BroadSim Wavefront. So we've been offering the BroadSim Wavefront now for a few years. And what we've had to date has been what we call Wavefront 1.0. And now we've made some major improvements to the system, and we now call that Wavefront 2.0. And that's what I'm going to talk about today, the improvements that we've made over 1.0 to 2.0. So first, let's get started with a review of the basics. Like, what is a wavefront? Why is it important that we have a different system to test that than other types of antennas? So here we have the view of just one RF wave, just one wave going along and hitting the antenna and the antenna elements. And that's happening at different times, right? So from the RF wave perspective, you can see we have to specially time it so that it acts like it's hitting those different antenna elements at the right time. If we can't do that, then the system won't understand what to do with the information that we're giving it. And if we look even again at, this is just another view from the RF wave perspective and from the antenna element perspective for multiple waves, right? Because we're not only working with a nice one wave at a time, that's just a demonstration. We have multiple waves coming in all the time. So you can see how as we add more, and this is just 4, that it gets a lot more complicated. And we have to accurately specify the timing between these different elements in order to reproduce an accurate simulation. So where we were is with Wavefront 1.0. So I'd like to review real quick what Wavefront 1.0 is. So first, it's built on the proven SkyDel simulation engine. As with all our BroadSims, we integrate SkyDel to do the GNSS signal generation. And that gives us the capabilities to do all of the things that we need for this environment. High dynamics, jamming, spoofing, repeating, plus everything that you would normally think about for testing GNSS. It's, just regular trajectories on the ground, space vehicle launches. We also support military encrypted codes, NavWare environments. We can do all of that with SkyDel. So you'll see with all of our BroadSim products, we integrate SkyDel inside. We do that the same thing with the Wavefront. But specific to the Wavefront, we have these multiple elements. So if we think of a SERPA antenna, let's think of one that has 8 elements. So we need to input a signal into each one of those elements, because each of those elements are their own little mini antenna that feeds down into some antenna electronics, which could be built into the device, or it could be separated into 2 pieces. But either way, that's still what's happening. We're taking 8 separate signals and feeding them into the same device. They have to be timed appropriately for them to actually be able to be used by those antenna electronics. So this is how we've done it in the past. We have, in addition to what you see here with the actual elements in the radios, we synchronize all of the radios with 10 megahertz and 1 PPS, and that's true for Wavefront 2.0 as well. This is just another demonstration of the architecture. We have one controller, really as many nodes as you want, and you can control everything from that single controller. So you're not having to go into each one. It's not like a bunch of separate simulators that I have to control. It's still just one image that you're looking at, and then a system is controlling all of those other nodes. One thing that we implemented in Wavefront 1.0 was the real-time monitoring and correction. So in real time, we're taking a feedback into the system to say, okay, do we need to adjust the phase alignment of these signals? How far have they gone out? And we want to keep them within a range so we can make corrections for them in real time. When we do that, we're really focusing here on the longer term alignment. So this is alignment with each phase of each signal to each other in like longer measurements. Like here, say we do the correction every 20 seconds. To me, when with a timing background, 20 seconds is a very, very long time when you're used to working in the nanosecond world. So when I say it's a long time, it's all relative, right? So this is what we do. So it allows us to compensate for temperature drift. You know, if someone moved a cable, it's going to change the phase. It's very sensitive. So this is what we're doing here, is correcting those. We're correcting the phase alignment. What we've learned, though, and where we are now, is that really the phase stability is important, or the phase alignment is important, but the phase stability is what really matters. So the phase alignment we can adjust. It's over a longer term. When the antenna electronics are actually using the information that's being sent, it's doing it in very small measurements, from like 1 microsecond to 1 second. So we need to be able to also control the phase stability between the signals, or of each signal, so that it maintains its stability over that measurement period that the antenna electronics would be taking. So in order to improve that, and then really we took a focus on phase stability, whereas previously we had been working only with the phase alignment. So here with the Wavefront 2.0, what we've done is added a shared LO, or shared local oscillator. So that in addition to the 10 megahertz and 1 PPS coming in, the shared LO will be the actual signal used by the radio to generate the frequencies. And that way, all of them are sharing the same one. And that's a major improvement that we've made here. So just a review on the phase alignment again, we can do a fairly good job. Here what we're looking at is the effects of two CW jamming signals. There's two CW signals 180 degrees apart. So we're taking two elements and we're comparing them to each other. One's 180 degrees out of the other. If everything's perfect, they will null each other out perfectly, right? We wouldn't have any residual left, but that's very, very hard to do. So this is what's showing, like, even if the power level is slightly different in those CW signals, then we can see it. That makes a difference too. But this is just for how we do it for our testing, so it's very clear. We can measure element to element to element, understand what's going on. So within Wavefront 1.0, we had our spec was 3 degrees. So everything was aligned. Like at any given moment, you can look at the signals, and we say typically there's going to be less than 3 degrees between any of them. They could go up to 6 degrees. So that's our max, right? We have our typical and a max spec. So we're going to have max. We've done some additional calibrations of our radios and added some radio lookup tables here in order to improve that to less than 1 degree typical, less than 2 degrees max. So that's what we're seeing here. Is you can see the max typical, max typical of Wavefront 1.0 and Wavefront 2.0. So you can see that improvement there. But what we really focused on was the phase stability. And this is where we can see a major improvement in the system. So we have now, looking at Wavefront 1.0, a half a degree typical, 1 degree max, which sounds great, but really want to get it as close as possible for the best improvement. And what we've been able to do by adding that shared LO and those lookup tables is improve the spec by 10 times. So our Wavefront 2.0 is 10 times better than the previous version because of those additions. And we can see that here on the chart. You can see typical and max for 1.0, and then typical and max for 2.0. And this is the sustained null depth. More is better. Yeah, the amount of signal power that the attenuation that the signal or that the antenna electronics can put so that you don't receive that signal anymore. So if you have like an 80 dB jammer over there, then you can only achieve a null depth of 50, you're still going to see, it's 30 dB of that signal going through. Okay, so you want these signals to be, as good as possible. We want to have the greatest null depth, especially since we're working with test equipment. We want to be able to ensure that our system is not the one limiting the test setup, right? We want to push the system that we're testing to its limits. So if it can achieve a 60 dB null, then we need to be able to ensure that our system's aligned well enough to do better than that, so they can push their system to the limit. That's kind of the point of testing. So you can see that 10 times better, and we've discovered this is really the most important spec. right? The SERPA electronics can compensate for some phase alignment errors, right? As long as they're stable, and that's what we're looking at here is the phase stability of each signal. Say like it needs to maintain its phase accurately over what we're saying is the shorter term time scales versus the phase stability, phase alignment, which was the longer term. I think this picture will be a lot easier to demonstrate this. Here we have the red dot up there is where the start of the signal was. So we're applying a CW signal 180 degrees out of phase. So in a perfect alignment that these things would align and cancel each other out perfectly. So we would see nothing left here. I mean, that's never going to happen. That, this perfect world doesn't exist. But theoretically, we can think of it that way. But what we also see here, due to the instability of the phase, is this, right? This actually comes out as phase noise when the signals are moving rapidly and unstable. And that's what we see here is this phase noise. That causes a lot of problems in the systems. So we can do now with 2.0, this is exactly the same test. We were getting 35 to 40 out of the old system as the null depth. Here we're looking at 62 dB null depth. So that's a huge improvement. And it really does start to push now their systems under test, to see how deep the nulls that they can get out of there. We can also see here that it's a lot more stable as well over time. So this is just some tests that we ran to say that, we did a lot of math and calculations to figure out how should these things work? What should we be getting when we enter these different variables? And then we did some actual measurements to say, how does that align with what we predicted? And you can see here between the two, this is what we actually measured and observed, and this was what we modeled, and they're very close. Right, so we think that what we're modeling is correct. And that helps us a lot to have confidence to improve the system. We can do the same thing with the improvements that we've made in Wavefront 2.0 and see that now that null depth has gone, over 60. The next null depth there was 65, almost 66 dB, and it also aligns very well with the model. So when we're playing with the stuff and seeing how it affects it in the model, we're fairly confident that that's going to translate into the system, and we can measure it to verify. And finally, this is kind of a summary of all of this with the phase stability. So again, phase stability, we're really looking at the stability of a single signal, but for our testing, we have to use two signals, two different elements, because we want to be able to create the null. That's why we say interchannel phase stability. But it's that same image we looked at earlier for the 2.0 measurement, but we can also now plot these graphs on there, right? Like what the internal LO was and what the external LO is for typical and max values. So where are you at here? So this would be our typical for Wavefront 2.0 and our max for 2.0. And this is the observed range when we did the actual measurements. And then this is the typical way up here for 1.0, and then the maximum for 1.0. And this is the observed range as well. So it's a much wider range. So all of these small improvements that we've made really make the system, as I said, 10 times better than the previous system. So the previous system works well with some types of antenna systems. We expect the Wavefront 2.0 to work well with all types of SERPA antenna systems. Some of them do some more advanced calculations that require this level of phase stability. And of course, as always, if you have any questions, you can ask anyone at Safran Federal Systems, but also hit me up. I love to talk about it. I hope you can get that. And